So in this talk, I'm going to discuss two models. ALSIS Online is going to model the land processes at the regional scale, and EcoPath with EcoSim is going to model the marine processes, again, at the regional scale of the overall Kimberley region. Now, referring back to the slide that Matt presented at the beginning, so we are talking about the top part of this plot. So we're talking about scales of roughly from a few hundred to a few thousand kilometers in both the marine environment and the land environment. And while both models build on the information from the biophysics and the oceanography, this is mostly input of a model. The actual processes that is modeled has to do with mostly with the ecology and the social economic component of the regional processes, and this is why these two plots are here on top. Because of this, these models also relate to a regional scope for what regards managing the overall region. And because of that, we chose a commensurate scale in time. So we are going to project our modeling result a few decades in time, starting from 2015 when we started the model up to 2050. Now, in particular, what we are trying to do in this project is asking a number of questions. First of all, what kind of stressor might the region undergo in the next few decades? And secondly, what kind of option do we have for management of the region at the regional scale? And given the combination of what might happen to the region and the management options we might adopt, how might the region respond by mid-century? So I will summarize, like every other modeler, I will summarize here in a few minutes a work that took 3 years by a team, here with all the names, to carry out, so I will have to go obviously quite quickly. But at this link here that it can be reached through the WAMSI website, you're going to find more detail about the models themselves, how we parameterized the model, how we validated the model, and the exact screen output of all the output for all the simulations. Has been, a fairly big team, but the star players from this project, because it was a modeling project, where the two modelers, so I would like to acknowledge in particular Brad Stafford for the modeling on the land domain, and Hector Lozano for the modeling with EcoPath with EcoSim on the marine environment. So in this figure, I try to summarize everything we have done and everything we have achieved during this project. And basically my presentation is taking you through this image. So in a project like this, the first thing we need to do is try to understand, build a conceptual understanding of how we think the system works. And as a result, which one are the most important components we need to go into the model, and which component we might keep away from the model. So we started from a description of a food web that is in the marine environment. The food web here comprises 59 functional groups. Each functional group represents one or more species. The functioning of the food web is a function of feeding relations between the functional groups and the biological characteristics like growth, mortality, production, and so on. The food web is located in the domain of the marine model. It is spatially explicit. Different parts of the model have different habitats, and as a result, a slightly different variation of the food web are located in the different parts of the model. Now, the food web is affected by external processes. Obviously, there is oceanography, currents, tides, and cyclone, but is also affected by what happens on land. And here is where the ALSIS model comes into, which is also spatially explicit. On land, we have geomorphological processes like erosion, we have hydrology with water flows and so on, but most important, we have people. People carry out the activities, they work in agriculture, mining, they change the environment by building ports and building roads and so on. And all these activities are accounted for. to basically reflect the impact that land processes exert on the food web, basically through the coastal processes. And this is mostly have to do with people presence on the coast and the marine environment, fishing, waste generation, and water flows in terms of pollutant, nutrients, and sediments. So the food web, the land processes, and the oceanography all act at a regional scale. But on top of that, at a global scale, of course, we have climate change. And here, the information we are using for, about climate change actually is the one that Minga just introduced you to. Now, climate change is going to impact our food web mainly through three pathways. One, which is directly by altering the biology and the behavior of the functional groups. And secondly, indirectly by altering the oceanographic process, as Minga just explained, and obviously affecting what's happening on land, in particular in terms of fire regime and precipitation regimes. So we need to account for all of these processes in our modeling. Now, the second part of the exercise was to talk to a number of stakeholders and basically agree on what might happen to the region in the next few decades. And almost everyone we spoke to is confident that the main stressors for the region will be climate change and economic development. Now, climate change and economic development are labels, they are not actually processes, and each of them includes a number of processes. But at the regional scale and the temporal scale we are discussing, the sub-processes are highly correlated. So for example, for climate change, we are talking about sea level rise and water temperature. At the local scale might not be the case, but at the regional scale, the two are highly correlated because sea level rise is a function of global warming itself. Similarly, for economic development at the regional level for 30 years and so on, it's extremely unlikely to have increase in economic development but no population growth, for example. So we assume this correlation within these two main stressors. And then we decided to define the scenario that we want to model in terms of different impact, low, medium to high, of each of these two stressors, and from the combination of all of this, we ended up having 18 scenarios to model. The exact definition and specification of all scenarios is available in our report and on the website. Similarly, we have a conversation with our stakeholders for the definition of the management strategies that we wanted to model. We agreed that at the regional level, management can be applied mostly through three tools, that is the extent of the parks and the sanctuary zones, the fishery regulation, and the impact on tourist activities on the coast. And once this has been clarified, we have defined 5 levels of regulation. Medium is more or less what's going on now. High is, of course, an increase, and then going down up to no regulation at all. When we were suggested to model no regulation at all, we were quite perplexed. But within 2 weeks, Trump won the election, and suddenly this management strategy here was reasonable to include in the model, unfortunately. Now, if we take a number of experts and stakeholders and we lock them in a room with a whiteboard, with a few days, we might come up with an agreement on a picture like this of how the system works and what might happen. So the conceptual understanding of this doesn't take too long to come up with, but the conceptual understanding does not have much predictability power. So if we need to choose between management option, we need to guess how the management option might play out, and that's where some kind of predictability is needed. And that's why we ended up building 2 computer models. But going from the conceptual model to the computer models takes, in our case, almost 2 years. And that's where the 2 modelers, Hector and Brad, and a little bit myself as well, had to go through hundreds of papers, reports, data repository, including a number of projects within this very program. in order to parameterize each component of the models. And in most cases, this means taking information that sometimes is qualitative, or sometimes may be dispersed through a number of publications, turning into a number, because that's what computer models need, but also as an indication of uncertainty for each parameter, which is then used by the model in order to do the Monte Carlo analysis and assess the sensitivity of the model to each parameter. So that's the part of the project that takes the longest to carry out. Okay, after all this done, then in a few months, it's possible to run everything, obtain hundreds of maps and time series, and then scratch our head and try to summarize the results. And here I'm going to give you just a very quick summary of the results. So let's start from studying the change in biomass of different functional groups as a function of the scenarios that might happen in the future. One thing that we notice is that some species, or functional groups, better say, are very sensitive to changing scenarios. So from one scenario to the other, the biomass can change a lot, while for other groups, the change is much lower. This has implication for management because the species that are most sensitive are the best candidate for monitoring because of their very sensitivity can be early indicator of system change or on what kind of scenario might be materializing. On the other hand, some species, doesn't matter what scenario happens, they always see the biomass decreases, and some other always sees the biomass increase. And this again has implication for management because it's going to tell us roughly what direction and what amplitude of response the system might give to management intervention. Or on the other hand, if we set a target, how strong the management intervention has to be in order to reach that target. So this was a commentary on each species individually. Now, this plot here discusses the behavior of a system level. So this is a time series. So we have here from 2015 to 2050. Now, this plot here, I don't have the time to go into the technicality, but it gives us an indication of how much the biomass distribution among all the functional groups changes compared to how the system was at the beginning of the simulation. So, of course, the change is zero at the beginning, and the higher it gets here, the more the system has changed. The black line is the mean over all the scenarios we model, and the ribbon gives an understanding of the variance between one scenario to the other. Now, the interesting thing here is that it doesn't matter what scenario we choose, so it doesn't matter where we are in the ribbon, the main behavior is more or less maintained. So we have an increase, then we go down a little bit, and then we go up again. So because this is affected little by the scenario, we have to conclude that this is an intrinsic property of a system. This is due to the internal dynamic of a food web. Now, the implication for management here comes from the observation which is mentioned in the literature in several books and papers, that changes in biomass within a food web can affect the stability and as a result the resilience of the food web to pressure. So if this is true, it also means that the resilience of a system to pressure depends not only on the magnitude of the pressure, but also on the timing, and in particular on the timing of the pressure in relation to the internal dynamics of the system. So this is a further complication for management. Now, this is fairly speculative, so it would be important to do more study on this. But if this turns out to be true, then it highlights the importance of monitoring at the system level, not just at the species level. Now, if we take the same measure that I just described before, and then we study the change in the system for each scenario, and we cluster them, the result of the clusters are the different colors here, we see that there is a quite clear horizontal layering. And what this suggests is that the impact from climate change on the system is much stronger than the impact from economic development. So here, Yes, sorry. And then if we do the same by studying the impact on our management strategies, we see that for very high climate impact, again, the climate impact almost overrides the strength of the management intervention. But for medium and low climate change, then there is some kind of graduation in the performance of management options going from high to low. Now, there are two implications for management here. One is that, of course, this is bad news because at the regional level, we cannot affect climate change, so we need to take it as it is, and climate change is going to constrain the amplitude of the impact that we are going to achieve by management options. On the other hand, as Ming pointed out, these scenarios are scenarios of CO2 emission, and as they have a very long delay, so there's a lot of inertia on climate change. It's one directional only, things can only get worse in the time scale we are studying. As a result, there is an opportunity to act ahead of time because it's extremely unlikely we are going to be caught by surprise by this. So this is an option for strategic rather than responsive management. Now, of course, most people are interested in the performance of the management strategies on each individual functional groups. And here, I can't go too much into details. All the information are on the website. We have all our time series. But for a few groups here, what we show is climate change high is red, medium is yellow, and low is green. The 5 bars here are high regulation from very low regulation. And more or less what we see by analyzing this is that, first of all, increasing more or less from 20 to 30% the size of the sanctuary zone has a beneficial impact on almost all functional groups and on the overall biomass of the food web. And that this is particularly true for sedentary species and species that are exploited commercially, like barramundi, snapper, emperor, or by recreational fishing. So going quickly, the last of the results I'm going to focus is that by studying the food web, we can realize that the main processes acting on the food web are bottom-up processes, and their strength is much higher than top-down processes. And this catches on some of the presentations from yesterday afternoon in recommending that seagrass and macroalgae assemblages are accounted for in our management plannings and in our parks. Okay, so we all know modeling is affected by uncertainty. Matt has explained that very well at the beginning of. Okay, don't worry. That is highlighted by Matt at the beginning of the section. This is even more true for our models because we are so complicated and we have so many parameters. So I won't go through this again, but in our report and in our website, we have tried to give a priority on the issue where we need more attention if we have the opportunity for monitoring and data collection. So we have a ranking on what aspect of the parameterization might have the biggest impact on the quality of the model and how easy it might be to collect more data or set up some monitoring. Hopefully this can be used to prioritize future work if there is the opportunity. And finally, I wanted to point out the legacy from the project. Don't worry, just don't worry. So the main legacy, sorry, I think there are 3 items. It's okay. There are 3 items mostly in the legacy. One is that beautiful picture that we just lost. That is the conceptual understanding, is basically what we learned about the system, about what might affect the system and how it might respond. Now, human beings have the tendency to forget how difficult it was to acquire knowledge, and as a result to take for granted what we know already, right? So some of what I showed might seem obvious, some other a little bit less obvious, but if you remember 4 years ago when we were getting together, the main talk was about how much we knew, but we knew very little about the region. Okay, so that picture is a kind of improvement on that knowing very little. The second legacy that I actually think is the most important is the input parameterization. That's the effort that I said took over 1 year for Brad and Eckford and Hector to go all through all the literature, turn that into numbers, assign uncertainty label to all input. So if we want to use the models, again, the input is there already. If we want to use other models, there will have to be some kind of translation to be done, but at least that information is quantitative as is available. The final legacy, obviously, are the two models. We took, as I said, more than 2 years to set them up, a few months to run them and get the results. That means that if we have more questions to ask the models, we can capitalize on the 2 years investment, and this time it's going to take less time, less effort to answer more questions. Thank you.
Thanks very much, Fabio. I know we're keeping you from coffee, and I really appreciate your persistence. I'm going to whisk you out and back in about 15 minutes so we can catch up a bit of time. But I just think before we finish, to thank us, particularly Matt and Fabio, for putting together that concise understanding of what modelling is and why we do it, and the rest of the modelling team, if you could just put your hands together for those.